Hello folks, I've been asked to do a video on Boltzmann distribution graphs. It's spec reference 3.2.2, which again is part of the syllabus that Mr. Wright taught you in year 12. Okay, so this diagram here is a Boltzmann distribution, and it, in its most simple terms, is a visual representation of the gas molecules in a reaction. So the area under this curve, those of you doing A-level maths will know that, is the total number of gas molecules involved in the reaction. And we've got the energy of those molecules along the bottom. So if we look at the shape, it has a bit of a skewed normal distribution. And I'm saying normal distribution because you've got a small number of molecules down here that have very little energy, and you've got a small number of molecules up here that have a higher energy. And the majority of the molecules are in the centre here, of either average energy or very close to the average energy. A couple of points to pick out when you're looking at a Boltzmann distribution. The first thing is that the line goes through the origin of the graph, and that's because no molecules have got zero energy. So when the energy is zero, the number of molecules is zero. I've already said that the area under the curve here is the total number of molecules involved in the reaction. And the other point is that the line here never actually reaches the x-axis, and that's because, as I've written here, there is no maximum energy for a molecule. So that line is never going to hit the x-axis. If we carried on and extrapolated that line, it would never actually touch the x-axis. So that's a Boltzmann distribution to show you the gas molecules. What you need to be able to do is to sketch and talk about how that Boltzmann distribution changes if the temperature changes or a catalyst is added. So on this graph here, T1 represents the initial graph that I showed you at a lower temperature. Oh, silly woman, I didn't talk about on here. Sorry, just go back to this one for a second. This dotted line here with EA represents the activation energy. And if we remember from GCSE, the activation energy is the minimum amount of energy that molecules need in order for the reaction to take place. So you can see that generally speaking, there's a very small number of molecules that have got the activation energy or higher. Sorry, I should have pointed that out. So back to this one. So T1, as I said, represents the reaction at a lower temperature, say room temperature. And as we said, the activation energy here has only got this tiny proportion of molecules that have got the activation energy or greater. T2, however, represents a higher temperature. Maybe we've heated it up to 50 or 60 degrees. There's a few points to notice. First of all, the line still goes through the origin, and it never reaches the x-axis again, like it did in the other. But what you'll notice is the peak of the graph is shifted to the right-hand side of the graph. However, the total area underneath it is exactly the same as this graph, as the first one. Now obviously the exam board in exam conditions aren't going to expect you to be able to produce a graph that's got exactly the same area. That would be a point that you could write about in your answer. So the total number of molecules hasn't changed, it's just the graph is now spread out over a greater area, over a greater width of the graph. But what it now means is that if we carry on that line for the activation energy, you can now see we've got a much greater proportion of the molecules have got the activation energy or higher. Now at GCSE, we talk about the fact that increasing the temperature increases the kinetic energy of the particles, and that's still something that you can talk about in an A-level answer. So the particles have got more energy. That means there's going to be more frequent collisions because the molecules are moving faster. It's actually the increased energy of the molecules which is more important than the increased frequency, but both of those things will happen, and therefore the rate of the reaction increases. So starts at the origin again, peak is to the right of the original peak, area under is exactly the same, but our activation energy now gives us a greater proportion of molecules. Then the other one you need to be able to talk about and draw is adding a catalyst. Depending on whether you'd studied trilogy at GCSE or triple, you might have been given slightly conflicting answers to what a catalyst does in a reaction. Just to be clear, when we add a catalyst to a reaction, at GCSE we sometimes talk about it lowering the activation energy. It doesn't simply lower the activation energy. What it does is provide an alternative pathway, and that alternative pathway has a lower activation energy. But all you need to do on your Boltzmann distribution diagram is move the activation energy line down, and we represent it with an EC to show that it's catalysed rather than the normal EA. But you can see that by introducing that catalyst, we've now got a greater proportion of molecules with the activation energy or higher. And that's all we need today.